Hello guys, welcome back to Maison African Motives, still on Electrotechnics and for working on DC machines as revisions. We are going to be focusing actually on DC machines. That is the November 2022 question paper. If you to check here, that was question number 3, direct current DC machines. 3.1, we are given what is the function of a pole core in a DC machine. So as you can see, this type of a question, they actually repeat and repeat these typical questions. So we discussed in our previous class that is it is actually used to hold, that is to hold or to strengthen the magnetic field in this case. So this one is used to hold the field windings. That is to hold the field windings, which we can simply give as to strengthen. So we said we can write this as to strengthen, the magnetic field in this case. So we are going to strengthen the magnetic field. That's the magnetic field in this case. So meaning we can just have any simpler part that you understand from these two. It's just one and the same thing, but the way that you understand, then you can take any part that you understand from this. Okay. If you are to check on 3.2, we were given what are the two methods of connecting field coils of a DC machine. So there are actually methods that can be used when you are connecting the field coils in this case, which means we have got issues. We have got this part separately excited, or it can be self-excited in this case. So let us just have this part. All right. So this can be a self excited, and also we can have a separately excited. All right. So remember, these are the methods. Okay. Then how can the field coils of a DC machine be connected? Take note. They are giving us with the self-excited, they are actually giving us a hint of what they needed from the first part of our question. All right. Anyways, these are some of the things which can actually happen. Okay. How can the field coils of a DC machine be connected with self-excited machine? So we can have this in series. So the method of the to connect now, that is, we can have this in series. We can have this in a series. We can connect this as a series connection. Then a parallel connection is the one that you refer to as a shunt. So this is a shunt connection, or we can have it as a compound. So a compound, that means you can have a combination of a series and a shunt. All right. So, or it can be, that is where we've got a long shunt, short shunt, and so forth, depending with what you'll be given them. 3.4, what is the chief purpose of a DC motor starter? When they are saying what is the chief purpose, that is the major purpose, what is the major purpose of a DC motor starter in this case? What is it that we are going to use it for? A DC motor start. All right. So this can actually be used. It can be used to reduce the high starting currents. Remember, when I talk about these DC motors, they've got a lot. The current is so high. So the moment we've got this now, we are talking about reducing the high starting currents. That's the placement of a motor now is there to reduce the high starting currents. Okay, to reduce the high starting current to an applicable value. This is just one and the same thing. All right, to an applicable value, you are reducing the current. This is just one and the same thing. So that is the major part that we are going to have, or the chief reason for us having what DC motor starter in this case. All right, then we are given on 3.5 what type of winding would be used for each of the following. We can talk about windings. We talk about those wave winding, lap winding. Okay, so they are saying what type of the winding would be used of the following. 3.51, a high voltage low current DC machine. So if you're dealing with a high voltage and the current is low, there we can apply a wave winding. All right. So there we are going to have a wave winding. Then for a high current, low voltage, there we are going to apply a lap winding in this case. All right. So here we've got a wave winding, a lap winding in this case. All right. Then let us check number 3.6, where we are given calculations that we need to work on. So this is a short shunt compound generator. Take note, we are dealing with a generator. The generator, like I always say that the generator, it generates current, is the one that is generating the current, so it gives out the current. Whilst a motor it takes in the current. This is what you need to know between these two. All right, so there we are given, it's not just a compound, it's a short shunt compound generator in this case. So if we are dealing with a short shunt, our diagram is like this. Okay, we are going to go to the question and take everything, but let me just show you the diagram, what we are simply referring, so that if we read this information, you understand. So you'll be given a winding. In this case, this one is just a series winding to the armature. So we are going to have here, like I said, this is a generator this time. Take note, here we are dealing with a generator. So a generator takes in, that is, it gives out it is generating the current. So it is going to give out the current in this case. All right, this is our armature resistor. Then this is connected in parallel to the shunt resistor. So like I said, that is our shunt, which is our field, our winding. In this case, we're talking about the winding in this case. All right, so that's connected in parallel. That's for a shunt, but we are told it's a short shunt. So like I was saying, this is a generator. So a generator is giving out, it is giving out the current. So the current here at the load is going out, like this. It is being generated and it gives out the load current in this case, which is opposite on a motor. Now a motor, it takes in the current. So this is what we have on these two. All right, so here we have got our terminal voltage. We are going to have our terminal voltage. Then here definitely there's going to be the generated EMF. Then this is our shunt resistor, our armature resistor. Then we've got our shunt resistor. In this case, this is the series field resistor that we are given, which is our SE. All right, so according to the information that we are given here, we are told that this is a short shunt compound generator that supplies a current of 210 amps. So this is our load current. It supplies, gives out. So meaning to say our current at the load is 210 amps. This is the current being supplied here of 210 amps. It has a shunt field resistance of 60 ohms. That is for the shunt in this case. So the shunt resistance is taken to be 60 ohms in this case, like I indicated here, that this is our shunt here. So this is where we are having 60 ohms. Then an armature resistance of 0.2 ohms. So this is our armature here. We have got 0.2 ohms. So the armature resistance, that's being 0.2 ohms. And the field resistance, this is for the field in this case, which is 0.07 ohms. So our field resistance, which is 0.07 ohms. Okay, so that is what we're given, the information that we have. So calculate the armature EMF, which is, we are talking about this generated EMF for the generator in this case, which is E. So we are asked to calculate our E, that is the one that we do not have, but given a terminal voltage of 200 volts. So we have got a terminal voltage of 240 volts in this case. So this is our terminal voltage here of 240 volts. So what can we do from this information? That is the question now that you need to ask yourself. All right, so what I want us to do now is to formulate, like, let us try to formulate from the information that we have. Okay, let us try to formulate a formula that is going to give us the armature EMF in this case. All right, so I want us to bring this here. We have listed everything now. So if you are to check, also assisted from our diagram, we have got, remember I was saying here we are going to have our armature current. It's it's supplying. So meaning to say the generator is supplying the current here. This current goes to the load. Another current goes to the shunt. All right, so like this is what you're going to have. All right, so if we are to take into consideration, we are going to have our generated EMF here being taken as the generated EMF being the current that is going to affect our armature. Here we've got if you take here, armature resistance and the armature current, they give us a voltage. There's a voltage drop that is going to happen here. That is from the armature current times the armature resistance. All right, which is being added to the voltage. So here we're going to have this. If we move on here, we are going to move on here. We are going to see that we are going to have this one in series with the load current in this case. So we are going to have the load current times the series resistor. Then if we move on from this point to this point, we are going to have the terminal voltage, which is our V. So this is the formula that we are going to use to calculate our generated EMF, which is taken from V plus the armature current times armature resistance, the load current times the series resistance. So let us check what we have. We have got the terminal voltage. We have got it here. The armature current, we do not have the armature current. The armature resistance, we have this. The load current, we have this. The series resistor, we have this. So the only part that is missing from our formula is the armature current. So let us think of calculating the armature current in this case. How can we calculate the armature current? All right. So if we take into consideration what I was saying about these currents, the current that is the armature current is the supply, in this case is the one that is supplying both the shunt and the load current. So it means we are going to have our armature current as the load current plus the shunt current, in this case from our Kirchhoff's laws. The current towards the junction is equal to the sum of the ones flowing away from the junction. So from this formula, what are we having? The load current, we have it. What about the shunt? We do not have. So it means we have to calculate the shunt current in this case. So let us put this aside so that we can end up with everything that we need. So in this case, we need to calculate, that is to calculate the shunt current in this case. All right. So where are we going to obtain or have our shunt current? From the shunt resistor. How can we apply this? All right, the voltage drop, so you're going to have this as the shunt current. Also, you're given this formula as the voltage plus the load current times the series resistance. This is voltage. We have got two voltages drop here all over the shunt resistance in this case. So that means we can calculate our shunt current. That is going to be V, which is our terminal voltage of 240 plus the load current in this case. From the load here, we've got 210. So this is 210 times the series resistor in this case of 0.07. So this is 0.07. All right, so we've got 0.07 like this, everything over the shunt resistor of 60 ohms. All right, so this means we are going to obtain our shunt current in this case. All right, so let us take this into consideration. That will be something like 4.245. So you're going to have 4.245 amps. All right. So having this is our shunt current. Remember, this was the missing value in order for us to obtain the armature current. Now we can determine our armature current. Our armature current is going to be the load current, which is our load current here is 210. So we are going to have 210 plus the shunt current, which is the one that we got here of 4.245 amps. So if we are to add everything, we are going to obtain our armature current in this case, which is going to be 214. So we are going to obtain 214.245. So that's 245 amps. So that's having this current, we are going to substitute now in this formula to calculate our generated EMF now. So all you need at this stage, all you need is just substitute. Okay, so that's the only thing. As long your formulas are there, all you need is to just substitute. So let us try by all means to get big this. I think we've got everything here. So we are going to have our E being equal to, so now we are calculating E. So calculate E in this case. All right. So we said our E is going to be equal to the terminal voltage, and we've got our terminal voltage. We said we've got our terminal voltage 240 volts, 240 volts. So that is our terminal voltage of 240 volts plus what was limiting us, which is the armature current. So we're going to have the armature current of 214,245 times the armature resistance in this case. So our armature resistance, that was from the information 0,2. So we are going to multiply to 0,2 plus the load current in this case. Remember the load current we are given, we had this one, the load current here, which was 210. All right, so we've got 210 here, 210 times the series resistor, which is our series field resistance of 0.07. So that's 0.07 ohms. So we are going to multiply to 0.07 like this. All right. So everything here is going to give us the E, which is our generated EMF. That is going to be something like 297,549 volts in this case. All right. So these are the steps, guys, that you need. As long you can apply these steps, you can actually have the full marks. All you need is to play around your formulas. As you can see, it's a subject that needs us to work with more formulas, how to play around with formulas and also your diagrams, all right, which is actually fine. All right, let us check the other part of a question, which was 3.7. On 3.7, we were given in this case that's a 6-pole lap connected armature. So, okay, that is what we have. And they've got calculate the suitable number of slots per number of conductors per slot. All right. So let us see what we've got here. The moment we are referring to the number of poles, 6 poles like this, we are going to find the P, which it represents to the pair poles. So these are the pair poles in this case. So meaning to say, out of 6 poles that we have, how many pairs we have divided by 2? That means we've got 3 pairs. So P is equal to 3. Then it's lap connected armature. For a lap, C is equal to 2P. If it is a wave, remember I said C is equal to 2 for a wave. So for a lap, that is going to be 2P, which is 2 times 3. Our P here we said is 3. So 2 times 3, that is going to give us 6. So C is equal to 6. It is driven at a speed of 300 revs per minute. That means we've got a speed of 300 revs per minute in this case is required to generate 200 feet to generate. That is the generated EMF that we are given there of 250 volts. The useful flux per pole is, so we've got the useful flux per pole, which is 0.07. If the armature has 115 slots, not conductors, but the slots, meaning to say, remember the slots are the ones that carries the conductors. So you can say number of conductors per slot. So meaning to say, if there are 115 slots, how many conductors are you going to have per each slot? All right. So here we are given the number of slots in this case. So we've got the number of slots, which is equivalent to 115. Then calculate the suitable number of conductors per slot. Now we need the number of conductors per slot. Remember, the number of conductors is given by Z for conductors. So we need like Z per stroke, per slot, I mean per slot in this case. So what is going to be the number of conductors per slot? That is our question in this case. So we need the number of conductors per slot. All right, so let us take this into consideration. Since we are talking about Z and we're talking about the number of slots, so let us just work on calculating the Z, because we've got Z representing number of conductors, and from the generated EMF, we have got this from our formula sheet. We are also given the generated EMF, which means there is no worry for us. But just to understand your formula is very, very important. Remember that the generated EMF is given in our formula sheet is given as 2Z NP times flux, in this case, over 60C, provided that this N is in revs per per minute if our N is in revs per minute. So what we need in this case is to focus on Z in this case. So let us make Z the subject. Remember I said change of subject is the core part of our syllabus. So make Z the subject. All right, so we're going to make Z the subject of the formula in this case. That means we can cross multiply since this is over 1. So 60 is going to multiply this side. So if we multiply 60C times E, we are going to have 60CE, which is equal to 1 times this part. We are going to have 2ZN P times flux, which is the number of the number of conductors can be calculated from this Z. So you can divide by everything. We can divide by 2 N, P, and flux. So if we divide by these here, we are going to cancel, meaning to say we're going to remain with this Z here. So meaning to say our Z is going to be 60 CE. Remember, you have divided by this both sides. We're going to divide by 2 N times P times the useful flux like this. All right. So this is what is going to give us the number, like all the conductors that we have. Then we can talk about the conductors per slot after that. All right. So now let us substitute because we've got these from our information. So our Z is going to be 60 times C. Remember I said it's for a lap where C is equal to 2P and we got our C, which is equal to 6. So C in this case is going to be 6 times the generated EMF. We are given the generated EMF, which is 250 volts in this case. So we are going to multiply to 250 volts, everything over 2 times the speed. Remember, the speed is in revs per minute in this case, since we've got this 60 here. So meaning to say we are going to use our speed N in revs per minute, which is 300. So we are going to have 300 in this case times. We are now on the pair poles, P, the number of pairs that we have. We said our P here is going to give us a 3. So after dividing, we are going to remain with the 3 pairs times the useful flux in Webers. In this case, our useful flux is given. Our useful flux, I didn't list it here. Why? But we are given this here. The useful flux per pole is 0. Okay, here I listed here 0.07. All right, so we listed this. All right, so that's 0.07. So we've got 0.07 in this case. All right, so this is going to give us the number of conductors that we have, which is it. So we are going to have something like 714,28, which is talking about the number of conductors. In this case, we can write as 714 as a whole number. So meaning to say we have got 714 conductors in this case. But this is not our question. This is not our question, guys. If there are 714 conductors, therefore, how many conductors are there per slot? The question is here. Let us take our question. The question is to calculate the number of the suitable number of conductors per slot. There are how many slots here? There are 115 slots. These 115 slots, they correspond together with the 714 conductors. So we've got 115 slots in this case. Each slot, how many conductors is it going to carry? That is the question. So we need number of conductors per slot. So what is going to be the number of conductors per slot? Per simply means over per. Like if we say kilometer per hour, we are saying how many kilometers are being traveled in an hour per. That is in an. So here we are talking about conductors per slot. So we are going to have 714 conductors. So these are 714 conductors over 115 slots. So we have got 115 slots in this case. All right. So if we divide, this is going to give us the conductors per slot in this case. All right. So thus we are going to divide 714 divided to 115. So if we divide 714 to 115, we are going to obtain 6.20 and so and so on and so on and so on to the nearest whole number. That is going to be 6 conductors per slot. So you've got 6 conductors per slot. So this is going to be 6 conductors per slot in this case. All right. So that is what you're going to have at the end. So that is how we can answer this typical question. Take note, it was not about the number of conductors, but the conductors that you have, the number of conductors per slot, meaning to say the slots, they are also included in your answer. Sometimes they might give you to calculate the generated EMF, whereas you are given number of slots and number of conductors. That is the number of conductors per slot. You multiply that to find all the conductors, which is Z. Like for in this case, we are given 6 conductors per slot, and there are 115 slots. You multiply 6 times 115. That is how you play around this type of a question. All right, so this is what we had, guys. It was actually 5 marks to answer this question, and everything 20 marks from this question paper on DC machines only. So this is actually a lot of marks that you can have in exam. To have 20 marks, it's a lot. So let us try to revise as many questions as we can as we prepare ourselves for the exams which are ahead of time. But for now, that's it from Amazon African Motives. Till we meet again.